may remember me from such well-known products. I worked on, and Matt and I together worked on the 4300 Iridium box. I worked on the Jaguar project that is going to be part of ATG 4G and UCS2. And although we don't, it's not that obvious. I actually have a little code running in the original UCS Classic too. I did some device driver work on that box. So I've got my handprints on a lot of stuff. And this is the same disclaimer I made when I made my last talk. I'm not a network engineer or a network architect. I'm a product developer. I actually get paid really good money to actually ship product, work product and ship it out and support it in the field and so forth. So when I talk about Internet Protocol version 6, my whole perspective on it is from the point of view is how does this affect the product work that I do. Now, if you really want to know about the architectural design and how the protocols work, I really have to defer to guys like John Kelly, you know, who are the, and your ground network people, because they're the real experts in that area. And so they have to keep me honest, too. If I say something just amazingly stupid, it's almost a given that that's going to happen. But the point is I'm really concerned about how the movement toward IPv6 affects the kind of things that I do for a living. So the best, I'm just going to tell you right now, the best slide in this entire presentation is this one. Okay, now this is kind of old data, and I actually came up with this slide. You see the dates. I actually did this, I've been updating it over the years, but it's kind of old data. But what this is it really shows on a logarithmic graph, you can see these are powers of 10s here, the growth rate of different types of technology. And this is a little hard to read because Excel helpfully, some of these things have the same growth rates, so the lines are actually on top of each other, so it's kind of hard to see some of them. But the one I really want you to see is this one, is internet connectivity. Okay, it's bigger than any of the other ones for a few reasons. The growth in internet connectivity has been driven by the explosion in, for one thing, Moore's Law, right? Made computers cheap, made a lot of the components in networking cheap. The mobile device explosion that came out of that means everybody's carrying a network-connected computer in their pocket, but also devices have multiple network connections. You know, back when IP version 4, which is the version of the Internet Protocol that you're all using all the time, whether you realize it or not, back when that was first invented, no one could really conceive of anything but maybe a router needing more than 2 network interfaces. But the fact is, everything has more than one network interface now. Your phone has a Wi-Fi and a wireless mobile network interface. Your laptop has a Wi-Fi and a LAN interface, a wired interface, and may actually have a cellular interface, may have 3 network interfaces. And all those things have their own IP address, and they're all on separate networks with separate IP address ranges. So, you know, this explosion has happened for a lot of reasons. But one of the reasons this happened was because of these other curves. You know, we've seen an explosive exponential growth of CPU cores and memory size and microprocessor speed. And all of these things came together to make, if not make this curve expand at this rate, at least make it possible to expand at this rate. Now, if you really want, this is just sort of an example thing here, but if you really want to know what the actual growth in internet growth has been, this is somebody else's chart, also logarithmic curve, all the way from 1970 and the birth of the early internet, before actually IP actually existed, when it was a project from the Advanced Research Projects Agency, to the present day. And we'll see that it's not quite a straight line like I represented it, but it's still a pretty sharp increase. Okay. So IPv4, that's the one we all use, whether we realize it or not. Internet Protocol version 4 was actually developed during about a decade period from 74 to 83, and it uses 32-bit addresses to uniquely identify every device or every interface on a network. And 32 bits, that's about 4 billion possible addresses. Well, In 1974, no one could conceive of devices having more than one network interface or really having more than 4 billion devices. The whole purpose of the Internet Protocol was a DARPA project to have a protocol that could survive a nuclear war. That's really what it was about. The whole idea of routing was to route around cities as they're being destroyed by Russian megaton warheads coming in on parabolic trajectories. Okay? That's what it was all about. And in fact, it actually works. You can actually nuke Chicago, and the internet will actually route around it. Okay? So the 132-bit address identifies the network, and if you have subnetworks within the network, it identifies the subnetwork and the host. And it's conventionally written, by convention, as 4 octets, that's 4 8-bit numbers, in decimal separated by periods. And that's an actual IPv4 address. I'm trying to remember what it is. I think it's my IPv4 Verizon address. And this will crop up later. If you want to use domain names instead of addresses, you didn't remind me. Yeah?
My bad.
Yeah, okay. So now I'm actually being recorded. So the first part of this is going to be strangely silent. If you use DNS and you try to resolve a domain name, the type of record you want to look at, this will become important later, even though it seems like a real detail now, is a DNS record type A, and that's A for address. So if you go out to DNS to look up dive.com, my company's domain, whether you know it or not, it's fetching a type A record for dive.com out of some database on some DNS server. So how do people actually get IP addresses, IPv4 addresses? Well, in the beginning, there was an organization which still exists called the IANA, the Internet Assigned Numbers Authority. And in fact, way back in '95, my company actually had a Class C address range, which was ridiculously overkill for what I wanted to do, but this was actually before most of the internet actually existed, okay? And so the IANA would give out blocks of addresses to internet service providers who would then feed them out to their customers. But as the internet became less about surviving a nuclear war and became more about actually ordering stuff off Amazon.com, that became a problem because a lot of countries wanted internet addresses, but they kind of didn't really want to have to depend on an organization that's essentially an agency, the US Department of Defense, to get an internet address. So this became a big political issue. So they actually split the entire block of 4 billion addresses, the ones that hadn't been used yet, and started giving them out to different regional organizations. Now, they didn't give them all out at one time. The way this works is the IANA assigns a big block of addresses to these different internet organizations in these different geographic regions, and then they split that block up into smaller blocks and hand them out. So you can see there's an organization for North America, that's the ARIN, one for Asia and Pacific, Latin America, Caribbean, RIPE is the European one, and Africa. So these guys all have their own blocks of IP addresses that they're giving out, and people monitor very closely because there's only 4 billion of them. You can't make any more, right? It's just 4 billion addresses. So people are monitoring very closely the rate at which these addresses are used up. And in fact, there's websites you can go to that'll tell you the rate at which these addresses are being used. Well, that is not good. This is actually from a few months ago. So the IANA has given out all of the IPv4 blocks to the individual regional geographic organizations. And here you can see how many they have left. And you notice this is the North American organization. So I don't really like that number. That makes me nervous. So, and yet, probably yesterday somebody went to Best Buy and bought a new router for their new apartment or their new home, and they hooked it up, and they got an IPv4 address from Comcast or US West or whoever their internet service provider was, and all the devices on their network have IP addresses. So how the heck is this happening? Well, it's happening through a number of reasons. One is IP addresses actually get recycled in the sense that if an internet service provider actually goes out of business, they can actually turn those address blocks back in and they'll get reassigned. The other thing that's happened is there's actually a free market now in internet addresses, and there are internet address block brokers. And in fact, Microsoft will pay anywhere from hundreds of thousands to millions of dollars for address ranges from other companies that have them that aren't using them. And that actually happens all the time. And so you can actually make money by hoarding IPv4 addresses. That's how short we are of them. But the third way, and it's really predominantly the most common way that we create more IPv4 addresses, we cheat. So if you looked at my home network, and I'm not going to take the time to explain all this, but some of this will seem familiar. Like here's the big internet cloud. Here's Comcast, who is my home internet service provider. And this is just my Asus Wi-Fi router that's sitting in my family room on top of the stereo cabinet, okay? So every network has an address range, like my test network for IPv6 is 192.168.2, my home network is 192.168.1, and every device on these networks has an IP address in this range. In fact, Comcast, the Comcast router that I talk to is 73.3.192.1, and my router was assigned this address, 73.3.193.194. On the other side of this, it has this address, and you can see these devices are all in this range. This router has this address, and these devices are all in this range. Except the funny thing is, if I went to Joe's home and looked at his router, it would also have this address. Well, I'll be damned. And if I went to your home and looked at your router, you would be using my IPv4 address, 192.168.1.1, and so are you, right? Okay, so the thing of it is someone's going to say, well, actually, mine isn't, but if you just take it out of the box and don't change it, chances are good. All of your routers are on your internal network using this address, just because that's the default one. When you take it out of the box, you don't change anything. So what madness is this? Well, these are all private addresses. They only mean something on your internal network, which means that whenever you go out to the network and order something off Amazon.com or use any kind of service that goes out, somehow this address has to get translated into a globally routable address that people know how to get to. Because if you're out here and you try to ping this address, there are billions of 192.168.1.1s. Okay, everybody's home has one, which means that can't be how it works. So the way we're cheating, and again, this is like more detail than anybody really wants, but there's another set of numbers which don't have to do with IP. They have to do with the application layer protocols or connection protocols that sit on top of IP, specifically transmission control protocol and user datagram protocol. And don't panic, I'm not actually going to tell you how those work because we don't care. But they have another thing called a port number, a 16-bit number. 16 bits means there's about 65,000 possibilities. And the original purpose back in the 1970s and 80s when they designed all this is that is supposed to identify a particular connection on, it's actually on a particular IP address, but effectively it's on a particular computer. On a particular computer, for example, port number 80 is always a web server. That's unless you're violating the standard. So whenever you type in www.amazon.com, the www.amazon.com gets translated by DNS into an IP address, but whether you realize it or not, your web browser is always going to port 80 at that address, where there will be some web server listening for a connection. So that was the original intent. So if we had real IP addresses that were globally routable, you could go from this system to this system, and your packets, the router would just be what Doug Young likes to call a bucket brigade. So the router literally does this. It looks at your packet, looks at the address, says, oh, okay, I know what route that goes to, and he writes it out to another network port. And he takes packets coming the other way and looks at the address, and hands them out going to another network port. And if we had enough IP addresses, that's the way everything would work. That's not how everything works, honestly. Instead, we have to use something called, and a lot of you are like, oh yeah, I've heard these terms, network address translation and port forwarding. What network address translation is the only thing that actually has a real live address is your Comcast router, the thing that talks to Comcast. And instead of addressing this device, you're actually sending it to the address of the router, to a particular port number. And in fact, these port numbers all have to be lovingly handcrafted on the router. That is, somebody actually had to sit down, somebody paid a six-figure salary to sit down and write a rule that says anything that comes to the router that is addressed to port 5555, two things have to happen. The network address has to be translated to some hard-coded private address on the other side of the network that only the router knows about. And then it's forwarded to a port on that end device with a private address. And then packets going the other way have to be similarly translated, not because necessarily this is a private address, but because the return address, that is, this is who this came from, which I'm not showing here, also has to be translated so that as the packet comes back, it appears to come from the router, not from this device, because nobody knows what this device is. Okay? So this is what this is like. The router gets a package, and instead of just looking at the address label, it has to open it up, and it has to say, well, that's going to port 555. I put it in a different box, I write out a new address label, and then I route it. And then if a packet comes back, I have to open it up, I have to look back and say, oh yeah, that's going to that, back to the, I have to change the return address so it comes to me, not to the end device, and then I have to pack it back up in another box with another address label and send it out. This is really expensive. Okay, it's expensive in terms of CPU horsepower cycles on the router. It's expensive in terms of time. So everything runs slower and costs more money. It's worse than that. Because of course, chances are good, first of all, this happens on every single packet. Every single packet. Every time you type something into the web browser, all those packets have to be translated in this way, going out. All the stuff coming back from the web page all has to be translated in this way. Possibly thousands of packets a second for all the connections, because it happens on all the connections going in and out that have to go out to the real internet. Chances are really good that the other side is also doing natting and port forwarding, so it has to be done on the other side. And what's more is, at least on mobile networks, I've seen multiple layers of natting where you think you have a globally routable address, but in fact, it's just another private address range, and there's another natting router that router's connected to. So this is a huge problem, okay? This whole problem of not having globally routable addresses means we're going through this process many, many times just to order stuff from Amazon.com, okay, or anything else that uses the internet. In fact, it's so expensive that if you're a very large organization, you can actually run out of bandwidth on your router. Things slow down because you simply don't have enough cycles to do this translation in real time. Packets back up, okay? You can actually run out of buffer space in the router. And in fact, this is one of the reasons why really big routers used by internet service providers are 6 or 7 figure pieces of equipment. They're essentially specialized supercomputers with specialized hardware for memory lookup and router table management. Okay, these are really expensive devices. So the guys that architect in the internet protocol knew that this is a problem and that this couldn't go on. You know, we're simply limiting the scalability of the internet. And so they started working on IPv6. And here's the thing, IPv6 is not new. They started working on it again in about a decade period from 95 to 2005. And in fact, Linux as early as the 2.2 kernel, and I'm pretty sure I'm the only person in this room old enough to have actually hacked on the 2.2 kernel, because that's a long time ago. The Linux 2.2 kernel actually had an IPv6 protocol stack in it. Probably nobody used it in the US, but it had it, okay? So IPv6 addresses, this is a complete rethinking. Now, remember I talked about other protocols like TCP and UDP? For the most part, they really haven't changed. Okay, they really haven't changed. It's just the lower layer, the routing layer in the internet that's changed. So version 6 is a 128-bit address. You know, they could have doubled the address range by just adding 1 bit. Or they could have made it 4 billion times bigger by adding 32 more bits. But they cranked that puppy up to 11. Okay, so IPv6 addresses give you about 10 to the 38th power. A number so big we don't even have a word for it. It's just really big number, astonishingly big number. Possibilities for addresses. And although you can in fact split it up in different ways, a common convention is that we don't call it the network part now, we call it the prefix. The prefix is typically 48 bits, the subnetwork is 16 bits, and they call it the interface. Remember in the IPv4 world, they called that the host portion, because no one could conceive of an internet host having more than one interface, but now everybody's got a device with multiple interfaces. The interface part is 64 bits. Just the interface part that identifies a particular computer is twice as wide, or 4 billion times bigger than the entire IPv4 address space. So this is like some serious shit here, right? Okay, this is a really big number. And the reason why they made, this is so exciting, can't you tell? The reason they made the interface 64 bits is there's a lot of networking addresses that have nothing really to do with IP, that address individual devices at the hardware layer, like Ethernet uses MAC addresses, which is 48 bits. Most of those networking technologies use addresses that are 64 bits or less. So how do you translate one of those into an IPv6 address? You just drop it bit for bit into the interface part, append the prefix and the subnetwork part, and voila, you're done. There isn't any complicated network protocol to derive an IPv6, or you don't need one if you choose not to use one. You can actually directly use the hardware address as the interface portion of the address. It is conventionally written, IPv6 address, as 8 hextets, that's 8 16-bit numbers, in hexadecimal separated by colons, and this is an actual, Verizon happens to be IPv6 address. And I can tell you from experience that, I was mentioning this earlier if you were here already, you can look at an IPv4 address and keep it in your I can anyway, keep it in my short-term memory long enough to turn over and type it into something. There's no way you can remember this. Okay, so when you start using IPv6, you've got to start carrying a pad of paper around, okay, or a lab notebook. That's just the way it is. And if you look up a domain and you want the IPv6 address for that internet domain, it's a type AAAA address. And do you know why it's AAAA instead of A?
4 times 32 is 128.
That's right, because it's 4 times wider. That's the only reason. So it's not an acronym, it's just a joke. Okay. So I started seeing, IPv6 is actually, it's in every Linux system. If you look closely, you'll find out all your interfaces have IPv6 addresses. Maybe you're not using them. But it's actually starting to be very widely used, and it's being widely used in places that are really feeling the IPv6 crunch. High-performance systems are using it because they really want to get past all the translation overhead of the packets. So people running really high-speed networks are interested in it. Places with either large populations or high population density with a lot of mobile devices are using it. So we're seeing a lot of IPv6 in Asia and Europe. And we're seeing a lot of IPv6 in the mobile network. In fact, people like Verizon, T-Mobile, and I think AT&T has said this. They're simply saying, we're not supporting devices that don't do IPv6, period. That's just the way it is. Okay, whether we're using it now or not, we're going to be using it in the very near future. And in fact, it's the only thing we're going to use in the near future. So this is just one little corner of my home office here. I think at last count there were 11 Linux systems in this photograph. Not all of them are part of this talk, but many of them are. And in fact, most of the ones in this talk are on this little anti-static mat down here, which looks like this. So this is actually my test network, believe it or not. This is an Ethernet switch, which you can barely see here, and this is an Ethernet switch. This is actually an Ethernet switch in my home network. So this is the 192.168.1 network, which is exclusively IPv4. And this is my test network, IPv6 network. Dual stack, meaning you can talk either v4 or v6 over this Ethernet switch. This is my router. This project name was Roundhouse. Every time it's a code name. It has it's just a Raspberry Pi 2. There's nothing complicated about it. Running OpenWRT. Lots of people in this room know more about OpenWRT than I do because you're using it in some of the stuff you ship. This has 2 Ethernet interfaces, one to my home network, which is v4, one to this switch. And then I have a bunch of other Raspberry Pis that are, some of them are set up for some special purpose things. Zinc is a Raspberry Pi 3 that actually has a cable just to the IPv4 home network. Copper, bronze, and lead are both connected to this switch, as are some of my desktop devices that sort of run off the top of this picture here, like Mercury. We'll see that mentioned. And here's, this one's interesting. This is 10. This is a Raspberry Pi 3 with a Verizon modem. It's speaking IPv6, but only to the Verizon network. So it's not even on this network. It's on some network that it connects to by a cell tower somewhere in my neighborhood. And so this is what this network actually looks like. So here we see some things we already recognize. Lead, bronze, and copper connected to that IPv6, that Ethernet switch that's my IPv6 test network. This is one of my development systems. It's an Ubuntu desktop. It has 2 Ethernet switches, or 2 Ethernet connections, one to the test network, one to my home network. Zinc is that red and white system that's only connected to the home network. This is the Raspberry Pi that's the router, running OpenWRT. This is my Wi-Fi access point and router that sits in my family room that connects to Comcast, which is how I get to the internet. But I'm actually using 3 different internet service providers. So here's 10, also sitting on my desk, with its LTE modem, connects to the mobile network, to Verizon Wireless. And then there's this other internet service provider. Hurricane Electric's an ISP that, for free, will set up their what's called an IPv6 tunnel provider. They will, for free, allow you to set up a tunnel through IPv4 to a router, and then shove IPv6 packets through it. Now this is not the fastest thing in the world, okay? Shoving low-level IPv6 packets through an IPv4 socket, okay? But it works. And so these devices, they all think they're on the v6 internet. They do DNS for v6 addresses. They communicate with the outside world through v6. v6 is all they know, or all they have to know. They're all dual stacked, but they can do everything they want to do through v6. And this router handles the illusion that they're on an IPv6 wide area network. It packages everything in that tunnel, which goes all the way through to Hurricane Electric, that sends it out through the v6 internet, and then handles all the reverse path too. So for example, if 10, for example, was a client and lead were a server, v6 packets would go through the tunnel through the mobile internet, through Verizon Wireless, through the v6 internet, through Hurricane Electric, through the tunnel, through Comcast, through this path to the router, and then onto the LAN where they look like just regular old v6 packets. Okay, and it's really transparent to these guys that that's all is happening. Now, in production, you wouldn't do this, but considering this service is free, and I'm doing it all with like just a few $100s worth of equipment, it's dirt simple to set up a v6 test bed and actually start testing your own stuff to see if it works or not. I wouldn't make any voice calls over it, or try to do really big, FTP sessions or SCP or anything like that. But for the kind of testing I wanted to do as a product developer, this actually worked really well. So let's suppose I wanted to talk to Led. Let's go back. Let's suppose I wanted to talk to this server right up here. So how would I address that server? Well, turns out there's lots of ways we can address it. Led actually has, it runs dual stack, it runs both v4 and v6. So I could talk to it using an IPv4 address, and that would work. In fact, it does work. Or IPv6 has a way of stuffing v4 addresses into an IPv6 address. And the system actually sorts that all out for you. Okay, it says, oh, I get it, it's a v4, it's a v6 address, but he actually really wants to use the v4 protocol. And v6 has a way that you can abbreviate strings of zeros out, so you can actually write that address this way. Or you can do it old school. I actually set up on the router, the OpenWRT router, a firewall rule that uses the old school IPv4 network address translation and port forwarding. So this is the address of the router, and this is the port that I'm forwarding. So if I want to talk to this port, I can actually address it to the router, and it'll get to Led, the server. Or I could use one of these two addresses, which are DHCP version 6, what are called unique local addresses. They're only meaningful on the local LAN. They're essentially like a private address. But they're actually assigned by the router using a DHCP server for a v6 service. Or I could use this address. This is what's called, let's see if I can remember this, a link local address. A link local address is solely created by the router to talk to devices on the LAN that it talks to. Okay, so it's another form of private addressing. But for example, if I wanted to talk to a DNS server on the router, I could use this address. Or, if Led wanted to talk to himself, this is the equivalent in v6 of the loopback address, 127.0.0.1, except on IPv6, you can abbreviate it as just : 1, and that's the loopback address for v6. Or, I could use this address. All of these addresses point to Led. This is the address assigned by the router using the Hurricane Electric prefix. So the first 48 bits is the Hurricane Electric prefix for my network. The rest of it is the subnet, and it's actually Hurricane Electric. The way I did it, it's actually a 64-bit prefix. And then the second half, the 64 bits, is the local sort of interface address for Led. And all of these addresses in different contexts will get to the same place. So let's try that out. Let's just see how that works. Okay. So this is a screen snapshot. This is where the techies will be interested and everyone else can concentrate on their pizza. What I've done here is I'm running a server process, which I'll describe in a moment, on Led, that little Raspberry Pi. What I did is I ran it, and then I did a Control-Z in Bash, which suspends it but prints out the command, so you can see the output of it, and then see what command I did to do that. So here's the little tool I have, and of course if you know me, you know it's called something tool. It's called Internet Tool. And what I said is, I said, okay, Internet Tool, I want you to use IPv6. I want you to use UDP, because it can talk TCP also. I want you to listen on port 5555, and because I like to see what's going on, be verbose and print the stuff out. So that's what it did. These are the packets that it received from all the servers, and it prepends each one with a timestamp and the address that it came from. And because Led only uses IPv6, these are all, no matter how you're connecting to it, it all looks like it to Led, like an IPv6 address. So here's copper. Well, that's interesting. Copper is coming in on a v6 address that encapsulates a v4 address on the test LAN. You can tell that because it's got a 2 here. Zinc, which is only connected to my home network, is also coming in on a v6 address that encapsulates a v4 address. And it's on the .1, which is my home network. 10 is on the Verizon network, and indeed, its address is a globally routable Verizon address on the Verizon network. Mercury, which is my Ubuntu desktop, it's coming in on, and I didn't tell Internet Tool how to receive these things. I mean, I wrote the code, obviously, but I didn't say, I want you to receive everything from essentially the DHCP address, right? That's just what came through the protocol stack. That's the DHCP address. And you can see here that bronze is also coming in a .2 v4 address encapsulated in a v6. So what does the other end of these connections look like? And trust me, there's a point to all this. Just bear with me through a few more screenshots and you'll see it. So here's a server, Copper. Copper's running Internet Tool in client mode using IPv6, UDP, and I said, I want you to send to port 5555 on this address. Well, that is LED's IPv4 address on the test network. 10 is the LTE modem, the Verizon one. Use IPv6, use UDP, connect to the globally routable Hurricane Electric address, okay, port 5555. Mercury is the one that has an interface on, it's my development system, it has interfaces on both the V4 and the V6 LANs. I said use IPv6, but I want you to connect to the DHCP provided address on the local LAN. This one isn't globally routable, but it's a V6 address. And without me having to do anything, it was the DHCP address of Mercury that came through the protocol stack on the other side. I didn't expect that. I thought that was interesting. Bronze is interesting. Bronze is on the test network, but I said, you know, I don't want to use IPv6. Just use IPv4 UDP and connect through the static IP address, V4 address for it. And finally, Zinc is only on my home network, not on the V6 address at all. And this is the one that's old school. I said, I want you to send to the router to port 5555. And so this is the way everything works today, through network address translation and port forwarding. So everything that Zinc does has to be opened up, taken apart, repackaged, readdressed, and sent out again. But Zinc doesn't know anything about that. He's using the same mechanism almost everybody uses today. So this is the same diagram as before. So what's the point of this? The point is that all of these devices can reach a server, one server running one application with one listening socket, and they can connect through all these various topologies using different address forms, IPv4, IPv6. They can go through network address translation and port forwarding, or they can use globally routable addresses. And they can do all this without even having to know that LED just speaks IPv6, which means that if you wanted to, you could deploy an IPv6 server, still connect through it through your legacy devices out in the field that use network address translation and port forwarding and IPv4, or you could use IPv4 alone without network address translation and port forwarding, or you could use IPv6. But you don't have to run multiple servers if you do it right, if you code it right. Okay, so what I'm trying to describe is a transition mechanism for transition to IPv6. Now, why might you want to go to IPv6? Well, that's a good question. Only you can answer that question as to whether you want to. But if bandwidth is an issue, if throughput is an issue, if global routability is an issue, and that gets you something that you don't have before, you know, IPv6 is not the monster everyone thinks it is. You don't have to convert everything or worry about converting stuff in the field. Okay, you can do sort of what a boss of mine used to call oozing the solution, okay, a little bit at a time. So from practical terms, what does using IPv6 look like? Well, some of the commands change. Like instead of ping, use ping 6. Instead of traceroute, use traceroute 6. Some of the commands just have switches on them to indicate that you're giving them an IPv6 address instead of a version 4 address, like SSH IP. IP-6 neighbor show is sort of the version 6 equivalent of the ART command. And when you want to look at the ART cache, okay, wget has a -6 option. Route goes its own way. You have to say, I want to use the address family on that 6. And then route will put the route you specify into the correct place in the address table. If you want to look up a domain name using host or NS lookup, you have to specify the AAAA address type. Okay? And if you want to use, if you're using a web browser and you just type in a domain name, you won't even know whether it's using v4 or v6 or not. That's really up to DNS as to whether it returns a v4 or v6 address and what kind of a network you're currently on. But the new RFC for URLs says if you want to hard code an address, just like you would like an IPv4 address, you have to enclose the v6 address in square brackets. And so let's look at just a few examples of that. Here's IPv6 neighbor show, and one of the things I like about this is you can just type this in and see who else is on your LAN. And notice it shows, oops, push the wrong button here. These are all v6 addresses, some of which point to the same interface. You can only know that by correlating the hardware address of the MAC address of the Ethernet interface over here. For example, let's see, 5A, well, here's easy one, DC and DC. So this address and this address are actually the same device on the network. They're just two different IPv6 addresses. And here's a web browser. This is actually Safari running on Mercury. And this is the admin web page for the OpenWRT router. But notice, this is its address. I typed in, as an example, its address. This is the Hurricane Electric prefix plus ::1, which is the address of the router. So that's just how you would type it into the web browser if you're using a v6 hard-coded address. But there are a couple things I want to point out here. The router says, oh yeah, I've got two WAN connections. I have a v4 connection and a v6 connection. Well, you notice the v4 connection looks strangely familiar. It's got its own static address on the .1 network. It's got a net mask we sort of recognize. And there it is. That's my gateway, which is my access point router sitting in the family room on the stereo cabinet, 192.168.1.1. And I had to admin all this stuff. Here's the kind of cool part. IPv6 has the Hurricane Electric prefix plus the other end of the tunnel. And that's it. That's all I had to admin. All of this other stuff that usually you worry about having to set up, it turns out IPv6, if you choose to use it, is smart enough to auto-configure all this stuff for you. And we'll see that in just a second. If you like using Wireshark, and I know we have some Wireshark folks in the room that know a lot more about it than I do, Wireshark works with IPv6 just fine. You can see here's a snapshot of the test LAN. You can see both v4 and v6 addresses here. And the one I picked out to look at is something called a router advertisement. When a v6 host connects to a network and the network interface comes up, the first thing it does, it says, I think I'll send a router solicitation, which is saying, hey, are there any routers on this network that will talk to me? And the router zips a message back called a router advertisement. It says, yeah, I'm a router. I can talk to you. And in fact, here's my LAN address if you want to talk back to me. Here's some IPv6 prefixes, some networks that I know how to route to. Oh, you need a DNS server? Yeah, I have one of those too. Here's the link local address. Just send your DNS request to this and I'll resolve them. And of course, he just passes those along to the other end, to a Hurricane Electric DNS server, right? But that all happens automatically. I didn't have to add any of that stuff. There are websites. This is a web browser actually running on the Raspberry Pi using its web browser. Notice I just specified a domain name, so this got resolved to some address. I actually don't know if this is a v6 or v4 address, but it's a website, one of many that you can use that tests your IPv6 connectivity. So I just took one of the systems, I think it was actually LED, on the v6 network and said, okay, server out in our actual internet, tell me what you can tell me. And it said, and of course it's complicated. It runs actually JavaScript on your system and accesses a bunch of information and talks to a remote server. And it says, well, that's interesting. It looks like you've got an IPv4 address, and that's in a block owned by Comcast, which is correct. It said, that's interesting. It looks like you also have an IPv6 address, which happens to belong in a block controlled by Hurricane Electric, which is also correct. And it runs a bunch of tests and it says, I have good news. It looks like you can do everything you want to do over IPv6. Everything's going to work. You get a score of 10 out of 10. Okay? So once you get to this point, you're pretty confident your test bed is working pretty well. Now, I'm going to tell you the dark side to this. This approach, whether you're either using global routable networks on an actual IPv6 or you're using something like a hurricane electric tunnel, you're putting a big hole through your firewall. Because one of the things network address translation and port forwarding does is act as a kind of a firewall. Because you have to manually administer all these port forwarding rules, only things that have manually administered rules can actually get through your firewall to get to an end device. With IPv6, everything can be seen. Everything. So you really need to have, and I sweated this, okay? In fact, I was so paranoid that the hurricane electric tunnel that is in these slides, it's gone. Okay, so if you try to hack that network, it might exist, but it's not my house, okay? It's somebody else's house. I really sweated the firewall rules when I did this, and in fact, I did a lot of testing using tools like Nmap and probing tools to see if my firewall actually worked correctly. So I'm just warning you that the downside using IPv6, the plus side, you get global routability. The minus side is you get global routability, okay? Is that everyone can conceivably see your devices. That's a lot harder than it sounds because there's 10 to the 38th power different IPv6 addresses, whereas any of us could just rattle off 4 billion IPv4 addresses. That's easy. But 10 to the 38th, that's a big number. So it makes it much harder for people to hack your network, but it's not impossible. So if you're going to use IPv6, you really need to come up to speed on the firewall stuff. If you've been slacking off and relying on NAT and port forwarding to protect you, that's not going to work in this case. So you can do this too. Everything I've done is on GitHub. This is Roundhouse is the configuration for the router. So you could create your own OpenWRT image to do this same thing, which you would then admin with the information from Hurricane Electric, if you chose to do that, to set up your own IPv6 test network. And Internet Tool and the library that it's built on top of is also on GitHub. It's probably my oldest project. I've been working on it since 2008. So that's all available. You don't need to pay me. You don't need to talk to me. You don't even need to think about me. You could actually download this stuff and build it and set up your own IPv6 test bed and actually start playing around with this stuff right now. Now, the techies were sort of into all the addressing stuff and everything, but those of you that are architects and managers, this is the most important slide. Okay, it really is. This slide says a lot of things, but the big picture thing you really want to carry away from this is that when you design a product, starting at year one, you pick a selection of components to use, a networking technology, a processor, you size the memory, the amount of storage, and you try to come up with a balanced system. But 5 years from now, the components that you would use to design are going to be radically different. They're going to be faster, bigger, put different stresses on your company network, and so forth. Okay, and these things are all growing exponentially, and they're all growing at different rates. So you can't just take the architecture you had from 5 years before and say, we're just going to buy all new stuff and build this same product. It's just not going to work. Okay? Everything grows at an exponential rate, but they grow at different exponential rates. So everything's going to be different when you do that. So this is really, a lot of my architectural thinking is really all based around this chart. That's it. But wait, there's more. So be thinking about some questions while I do this here. I'll see if I can make this quickly. You knew that you weren't going to get away without a demo, right? You can talk among yourselves. All right. What's he doing? I don't know. This is probably, the print will be too small for anybody to see anything here. It's a miracle. So this is 10. This is the very client that you saw on my desktop with the Verizon LTE modem. It's talking to LED on my desktop right now. It's sending a packet to it through IPv6, through the Verizon network. It's going through all that stuff through the tunnel, through Hurricane. It's going through Verizon, then it's going through the Hurricane Electric tunnel, then it's going through Comcast, up through my home router, through the Open WRT router, through the LAN, the version 6, the V6 based LAN, to LED, which is sitting on my desktop running and turning those packets right about around again and sending them back. And so it's working. It's worked ever since I left my house today and packed it in that box. Okay, it's running on a battery pack. And it'll run for hours on this battery pack. Now the other interesting thing is, this is one of the reasons I like using UDP. Internet Tool can use TCP too. The interesting thing about this minus 73 is 10 remarking. That's interesting. The packet serial number that I sent out is 73 off from the one I got back. That's because there seems to be about a 1% loss in packets on the Verizon network. Okay, I don't see this on anything else, just on the stuff connecting through Verizon. Again, maybe not a big surprise, but I thought it was worth pointing out. So since I started this up and packaged it up to make the drive over here to give you this talk, I've lost 73 packets on it. So that's just something to think about. Okay, now questions. You're stunned, I can tell.
That's 10 sitting right over.
Yeah, that's it. That's it. Yes. Yes, that's it. That's all there is to it. It's a Raspberry Pi 3 running my software with a Verizon modem on it. And this is its only network connection. This is an Ethernet. This is the console serial port that I'm talking about here. So this is it.
So who hands out the IPv6 addresses?
It's same organizations. IANA gives out huge blocks, right, because it's got a big address range, to those different international organizations, those regional organizations. Then they give out blocks of addresses to internet service providers like Verizon, Comcast, okay? And then those guys give out, in my case it was a 64-bit prefix, to individual users. So who mentioned what Haroon said? He said that he has an IP address range, except now he has 4 billion of them. So yeah, I got, I can't even remember, what is 2 to the 64th? It's some really big number. But I got a range of that many addresses for me to use, okay, however I see fit on my V6 test network. And the address range is so mind-bogglingly big that Hurricane Electric will hand these out for a tunnel for free. Okay, that's how big this address range is. It used to be almost impossible to get IPv4 addresses. Now you can get billions and billions and billions of IPv6 addresses for nothing. Temporarily, anyway, as long as you have their tunnel set up.
So you're talking about security actually coming through your firewall?
Yes.
And so how do you actually start approaching that? Then do you actually have to start doing spy, SPI kind of stuff on individual packets and only routing specific?
Well, it's really not any different from the IPv4 firewall. It's the same firewall in the same router. It's just that now, before, you could kind of slack off on your firewall rules because NAT and PF actually blocked a lot of stuff for you. But the real truth is you should have been doing that firewall stuff all along. Now you really have to be doing the firewall stuff because there's nothing to stop someone from coming through and addressing individual devices on your network. Like, you're reading this stuff now about, your smart thermostat getting hacked, right? Or your internet-connected refrigerator getting hacked. This is even more possible now with IPv6. So you really need to be a lot smarter about the firewall stuff than you were before. But again, you should have been doing that all along. It was only because almost an accident of the way NAT is used to save IPv4 addresses that you were getting away without having a really good firewall. In V6, you can't really do that.
So technically, they could come through on a V6 device, and once inside your network, then,
Wreak havoc.
yeah.
Yeah.
Even with the IPv4 stuff.
Yeah, you really need to have really good firewalls with it. Because like I said, global routability, it's both good and bad.
So, okay, so 128 bits, right? That's considerably larger, but I guess I'm curious if you could speculate on the likelihood of coming out of that as well.
Who knows? Here's the problem. Remember that graph with the exponential curves? That's why that graph's important, because I assure you, the guys that started writing IPv4 in 1974 never anticipated all of us carrying, in a 64-bit ARM processor with multiple network connections in our pocket and thinking that it was just, I'll get the new one next year, that it could be that cheap. It's just, and so I'm not worried about it. But, if what you're saying is 20 years from now, are we going to have an IPv8? Maybe, I don't know.
Well, so they estimate that there's 10 to the 82 atoms in the known universe, observable universe.
Yeah.
So, like,
So we don't have enough, not quite enough addresses for every atom.
yeah.
So some of you are going to have to share. That's right. That's right. But it's a big number. And these guys, some of the same guys worked on both V4 and V6. By the way, there was a V5. It was an experimental thing. It was never intended for deployment. And, as I like to say, we shall never speak of it again. But some of the same guys worked on it. And that's one of the reasons they were under a lot of pressure to make IPv6 addresses 64 bits. Because that fits in a variable. Right, just like the 32-bit ones did. It would have been, frankly, made my life a lot easier if they'd done that, because now you can't just deal with an integer variable. You have to actually deal with like a structure or an array or something like that, and it really makes the coding, I'm not saying it's going to make it harder, there's just a lot more stuff you have to deal with now, remarkably more stuff you have to deal with when it's not a simple integer variable. But, they said the same thing you did. Look, we were wrong before. With 32 bits. We don't want to take that chance again, so we're going to just crank it up to 11, 120 bits. I think IPv6 is fascinating from an architectural point of view because it really shows how you can feel like you're right on the bleeding edge, and yet, in a way, you're a victim of your own success, right? You just totally fail to understand what's going to happen with the things that you build. Who would have guessed that we would run out of 4 billion addresses? Certainly in the 70s and 80s, this just never occurred to them. And yet it happened. I just think of, I like stuff like that. I think it's interesting.
On the regional, where they block that and give it away, has there any discussion on reallocating some of that? Because to me, it seems like usage demand.
It's already happened. That's exactly what's happened. Is people they've been taken away and reallocated, but it's clear that the end's in sight, right? Everybody's running out of addresses, so you can only do just so much.
Yeah.
But in fact, that has in fact happened. But you can imagine the political problem is you go to Africa and say, we want some of your IP addresses back. Well, that's like arguing with China about carbon sequestration. It's like, well, why us? You had the advantages of all the IP addresses you wanted all this time. Now you want to take some of ours, and you can imagine the political aspects of that. So.
Are they doing the same with the V6 though? Are they evenly allocated, or the regions changed, or?
I don't think so. My understanding is no, because the address space is so mind-bogglingly big. I just don't think they're worried about that right now. But they're not giving them all out. IANA still has the bulk of the addresses, and they're just handing out blocks as people need them. They don't allocate all of them all at once. Doug?
So you said Linux systems support V6 for years.
That's right.
How much of the other devices out there, like Microsoft-based devices, or
That's a good question. I've actually, on this same network, because I had the same question, I've actually hooked up a Windows 10 system, a Windows 7 system. My laptop runs Windows 7, and my Mac routinely runs on both networks, and I haven't had any problems. it seems to work just fine. Older, smaller devices, maybe they only speak version 4, but my guess is all the devices you're ever likely to use, that are not more than a few years old, you won't have any trouble